Hi everybody. Today we're talking about related rates. The goals of this presentation are as listed on this slide. I'm going to go over a methodology on how to solve related rate problems and guide you in the step-by-step solution on 4 related rate problems that I have selected. As with previous problems, the first thing you want to do is understand the problem. From there, you want to develop a mathematical model of the problem. Next, write an equation relating the variable whose rate of change you seek with the variables whose rate of change you know. Next, differentiate both sides of the equation implicitly with respect to time. You will probably have to use the chain rule here, so please be careful. And with the product rule, again, don't forget that second function. Fifth, substitute values for any quantities that depend on time. And the last thing is always interpret your solution. So our first example, the voltage V measured in volts, current I measured in amperes, and resistance R measured in ohms of an electric circuit like the one shown here are related by the equation V equals I times R. Suppose that V is increasing at a rate of 1 volt per second, while I is decreasing at a rate of 1/3 amp per second. Let T denote time in seconds. So the first two questions we're going to look at is how to get rates from the setup. First one we want to calculate is what is the value of the change in voltage over the change in time. Problem tells us that the voltage is increasing at 1 volt per second. So dV dt equals +1. The second rate we would like to look at is what is the value of di dt. Again, this is pulled from the problem. Notice that the problem says that the current is decreasing. That means di dt is negative. Continuing with this problem, the next question is find the rate at which R is changing when the volts equals 12, the current is 2 amps. Further, is R increasing or decreasing? Recall that voltage equals current times resistance. Might be a good idea to set up everything you know, to organize everything like I've done here. We're interested in computing dR dt, the rate of change for the resistance. We were given a change in voltage at 1, so dV dt equals 1. The change in current is -1/3. Voltage is 12 and current is 2 amps at this time. Going to rewrite the equation V equals IR as R equals V times I to the -1. Now I rewrite this because we're interested in dR dt. If I take the derivative of V equals I times R, my dR dt is going to be left on one side of the equation with many terms, and that's going to complicate the algebra. To make it easier going forward, I first solve for R, and I'm going to take the derivative of R. The derivative of the first function, V, is dV dt. I multiply that by the second function, I to the -1. Next, I add that to the derivative of the second times the first. For the derivative of the second, you're going to have to use chain rule. So the derivative of I to the -1 power is -1 I to the -2 times di dt. The last piece is multiplying it by the first function, so I add a v at the end. Once we have calculated the derivative of R with respect to time, it's time to plug in our numbers. Now before I plug them in, I'm going to make sure I have values for all the variables on the right-hand side. I has a value of 2, dV dt is 1, di dt is -1/3, and v equals 12. That means I have all the pieces that are needed to compute this rate of change of r. Here I plug in the numbers that I stated earlier. Using the calculator, I get that the change of r with respect to time is 3/2 ohms per second. Since this answer is positive, the resistance is increasing at that rate. On to example number 2. I'm going to look at 3 subproblems within this example. So values that we calculate in the first example and the second example will show up for the third piece. Suppose a 13-foot ladder is leaning against a house when its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. I have included a diagram of this situation. The y-axis is the house, whereas the x-axis is the ground. So the first question I want to look at: how fast is the top of the ladder sliding down the wall at that moment? In other words, we're interested in computing dy dt. At this moment in time, x is 12, dx dt is 5. I also have the equation x squared plus y squared equals 13 squared. And this is the Pythagorean theorem, with x representing the horizontal distance, y representing the vertical distance, and a hypotenuse of 13 feet. So using our x squared plus y squared equals 13 squared, we're going to take derivatives. We're interested in isolating dy dt. As with the previous example, I'm going to rewrite this problem just a little bit to make the derivative piece not as complicated. So x squared plus y squared equals 13 squared becomes y squared equals 169 minus x squared. Now that I have solved for y, it's time to take derivatives. Once again, we want to use chain rule. So the derivative of y squared is 2y times dy dt. On the right, the derivative of 169 is 0, so I don't write it. The derivative of negative x squared is negative 2x times dx dt. Finally, to isolate dy dt, I divide both sides by 2y and cancel out the 2's. So dy dt equals negative x over y times dx dt. At this point, I want to make sure I have all values for all my variables. X is 12, y we don't have, and dx dt equals 5. So at this point, you want to take a look at any previous equations you have and figure out if you can compute a value for y. Y turns out to be 5 using this equation. Y squared equals 169 minus x squared. I plug in x equals 12, and 169 minus 12 squared is 25. Taking square roots yields a value of 5 for y. Finally, I can plug in all my numbers and come up with a value of negative 12 for dy dt. dy dt is negative because the top of the ladder is falling towards the ground, and I've defined the ground as 0. So this is where that negative sign comes into play. Second subproblem using the same setup. At what rate is the area of the triangle formed by the ladder, the wall, and the ground changing at that moment? Again, I'm going to organize what I want and what I know. So I want to compute the change in area with respect to time. So dA dt. I know that x is 12, dx dt is 5, y is 5, computed it earlier, and dy dt is negative 12. I also write a new equation relating x and y, this time the area equation. So the area of a triangle, which is what the ladder is forming against the wall and the ground. The area is base, which is x, times y, which is the height, all divided by 2. So the area is 1/2 xy. Okay, so going to take the derivative of a with respect to time. This time, I do not need to rewrite it as I have isolated a already. The derivative of a with respect to time is dA dt. Going to have to use a product rule. So this becomes 1/2 times the derivative of x, which is dx dt, times y, plus 1/2 times the derivative of y with respect to time, times x. Next, I check all the variables on the right-hand side to see if I have a value. So for dx dt, I know that's 5. For y, that is 5 as well. dy dt is -12, and x is 12. So all the pieces on the right-hand side, I know I have a value for them. So I just plug them in and use my calculator to get a dA dt of -119 over 2 square feet per second. So the area of the triangle is decreasing at a rate of 59.5 square feet per second. It's decreasing because the answer turned out to be negative. So the last example for this video is as follows. At what rate is the angle theta between the ladder and the ground changing at that moment? Again, going to organize what I want and what is given or what I know. So I want to compute d theta dt. I know that x equals 12, that dx dt is 5, that y equals 5, that dy dt equals -12. As with previous examples, I need to come up with an expression that has theta, x and y in it. This time, the expression is the tangent of theta equals y over x. That's simply SOHCAHTOA. So from angle theta, the opposite side is y, the adjacent side is x, so tangent of theta is y over x. Now to the calculus piece. First, I'm going to rewrite tangent theta equals y over x as tangent theta equals y times x to the -1. This is to avoid quotient rule. Okay. The derivative of tangent is secant squared theta times d theta dt. Remember to apply chain rule. The derivative of y times x to the -1 is x to the -1 times dy dt minus 1x to the -2 times dx dt. Those three terms, -1, x to the -2, and dx dt, are the derivative of x to the -1, and then times y in the end. Now this one will still, or is going to require a little bit of work because we want to isolate d theta dt. So my first rewrite of this derivative is to change secant squared as 1 over cosine squared. This is a trig identity. On the right-hand side, I'm going to clean up this derivative. First, I factor out an x to the -1, so that comes outside. This first term becomes dy dt. I'm going to bring this y to the front and change this x or drop it down to the denominator instead of having it as an exponent. So this is the first rewrite. Next, I want to multiply both sides of the equation by cosine squared. So multiplying both sides of the equation by cosine squared theta leaves cosine squared theta divided by x. So again, changing this x to the -1 and put it in the denominator, minus this second term which we had cleaned up earlier. All right, time to check all our variables, see if we have all the pieces. First term, cosine squared theta. I do not have theta. So as before, we're going to look at our equations and see if there's an equation that has theta in it and we can use to compute a value for theta. We're going to use this. Tangent theta equals y over x. We know that y is 5. We know that x is 12. So tangent theta equals 5 over 12. To get to get theta by itself, I take the arctan of both sides, and I get this value for theta. Now, this is in radians. So if you are practicing this at home or wherever you're practicing this, make sure to change your mode to radian. If you have it in degree, you will not be seeing this answer. Okay? So theta is then equal to 0.3948. So we do have theta. X is 12. dy dt is 5. Y is 5. And dx dt is 5. Excuse me, I think I said 5 for dy dt. dy dt is negative 12, as is clear up here. Plugging in all the numbers, and you will get an equation like this. At this point, you obviously want to use the calculator. Now, I forgot to mention this. This value for theta, you probably want to store that as one of your values, is either a or x or whatever you choose. So you can use that in this expression of d theta dt. Okay, if you type in cosine squared of 0.3948, you will get a number very close to the answer, but it will be slightly off due to rounding errors. Now, if you plug it in correctly, you should get a value of -1. That means that the angle theta is decreasing at a rate of 1 radian per second at that moment in time. And for my last slide, I would like to give you this assignment. I would like you to try it, see if you're able to figure it out. We will talk about it tomorrow at the start of class. All right, guys, have a good day. Goodbye. Actually, like, share, subscribe. All right, guys. See you later. Bye.